Good morning, everyone. This is Keith Sinclair from Opmantic. I'm the Opmantic CTO and NMIS founder, and I'll be conducting the GoToMeeting this morning. If you have any questions, please put them through in the chat. I'll see those here and open up for questions, but we'll open up for questions at the end. That's probably the easiest thing to do. So we'll get started straight away. Hopefully everyone is seeing my screen now. So here today we're going to be talking about NMIS device modeling and the benefits and cool things that you can do with NMIS device modeling. So the agenda today is we're going to run through a quick overview, and we're going to be looking at how SNMP MIBs work, which is a fundamental thing, generally speaking, to collecting data. With NMIS, we can collect other sorts of data as well, but SNMP data is the most common data protocol we use. How we're going to add a new device type. We're going to be looking at adding a new metric, something that you might want to collect, adding a new system section or a system health section, and then adding thresholding and some other advanced features, and then we'll just look at some running and troubleshooting a model.
Hi Keith, we're not seeing your screen yet.
Yeah, here it is. Thanks, Mark. Not used to this GoToWebinar thing. So I'll go back to the agenda. So there's our agenda. If you want to get involved in the Opmantic community, you can head along to community.opmantic.com. We've got a great wiki page there. We've got the community forums where you can ask questions. You can search that really easily as well. And there's all of our documentation for all of the products, the open source and commercial products is all on the Opmantic community wiki. So why does NMIS have a modeling system? Modeling is a primary way that we abstract data. Essential to all computer systems is some form of abstraction, dealing with the things that they have to deal with, and NMIS has many things that assist this, but when we talk to devices, we need to talk to devices in a consistent way, and we want to be able to normalize the data as much as we can. So the modeling system is our fundamental abstraction system for communicating with things that we want to talk to. NMIS models are modular and can be reused, so you can write a section of a model, for example, the entity MIB, and then now you can just include and use that for other devices. And that's very important so that you don't have to continually rewrite models, especially with SNMP, given that large parts of SNMP are standards-based. So you can model something once and then reuse it again in different devices and sometimes even across vendors. So for example, the host resource MIB is widely used in many vendors for things like CPU load, disk usage, and things related to performance. And modeling can actually also normalize the way we collect data from different types of devices. So many different vendors back in the old days used to use different MIBs for CPU, and the CPU data is and stored in all sorts of different MIBs. So for example, Cisco will use average busy5, and other vendors would use a different MIB name. So the great thing about the modeling system is that I can normalize that if I choose to. I can normalize those names. I'm still collecting something using the vendor-specific SNMP OID, but I'm storing it in the database just called CPU load or CPU usage. I'm able to just normalize the data and use it internally the same way. Modeling also supports collecting data in just about any way. You can use data, collect data in different protocols, things like netconf, and use an NMIS. And to support that, we've got WMI, for example. So we support SNMP and WMI, and then through the plugin system, we support just about everything that you can imagine to collect data and store it in NMIS. So basically the NMIS architecture, software architecture, is fairly straightforward. we talk to nodes. We do that through several daemons. We have an NMIS daemon, the fping daemon, and the IPSLA daemon. We take data and we store that in several different folders. So we have the database directory, the var directory, and of course we have logs. And then we use abstraction to abstract things out. So device communication is abstracted through sys, which really uses models, and NMIS itself is abstracted through configuration and several other mechanisms like the notification system and several other policies and configuration options that NMIS uses, and that's all done through the .conf directory. And the user interface is delivered through CGI and a bit of JavaScript. So that's a quick summary of how the NMIS system works. So you're sort of looking in various directories, a CGI bin, the bin directory, and the lib directory for all of the relevant files. And then the data is actually stored in separate directories, the database, var, and logs directories. So what types of model files are there in the system? So when we're dealing, the main and the first model file is called model.nmis. It's the one that kind of bootstraps everything together, and it has the auto discovery rules which help us to discover new devices. The common models mean just that, they're common, they can be used by different other things. So we've abstracted the abstraction, if you like, but they're the header files or the include files. They're the ones that you would name and reuse. Graph files are quite obviously the graph definitions, and then the model files themselves begin with the word model. So you can see all of those in there. And then in the conf directory is this file called enterprise.nmis, which is actually used for just identifying the vendor using the SNMP IANA number for enterprises. So we call that the enterprises. And then once we've actually talked to a device and collected all the data and stored it, we use these two files, a node name. So if your router is called router1, there'll be a file in the var directory called router1-node.json, and there'll be a view file. The node file has all of the data that we're using and collected, cached in it, and that's all of the sort of the current data, all the performance data stored in the RRDs in the relevant folder. So they're all the files that are important to modeling. So how does modeling work? The first thing that you want to be able to do is it collects a sys description, a sys object ID from a device. This is the bootstrap process by how we're using a model. Then we determine the vendor. So we then look up the sys object ID and we determine who the vendor is from the enterprises. So we just get the first number of octets from the sys object ID, and that tells us who the vendor is using the enterprises assigned numbers. Then we basically look up that vendor name and we look up the sys description in the models.nmis, and that tells us what model to use. And then we load that model. So once we know that the vendor's Cisco and that it contained the word Cisco iOS, we now load the model relevant to that that matched for us in the rules. Now, once we've loaded the model, now we load the data. So now that the system would now load the device-specific information, which is cached in var. So that's how models are used inside the system. All of that happens in a heartbeat, and it happens quite a lot in NMIS. And we've done lots of optimizations to improve the performance and do things for in NMIS to make that work really, really well. And it's super fast. So let's go through how that sort of works and the data that it collects and how that happens. So the first thing that NMIS does is it does a sys description. In this case, we're looking at a Windows device. So we've got a sys description. We see that text there, Windows version 6.1. Then we get the sys object ID, and we're seeing those numbers there, 136141311. That's the vendor ID for Microsoft. So now we know that the vendor is Microsoft. Now we're looking through the sys description in the models.nmis, and we're looking for a match. And in this case, we want to match Windows version 6.1. That tells us now that the model is Windows 2008. So now we're going to load the model file, Windows 2008. So we go look in that model file. So we've loaded up the model file, Windows 2008, and it's told us to go load those common models. And so we go ahead and load all of those common models, and then we load the other main sections, so system interface, storage, device, system health, other things that we have to load. We go ahead and we load all of those. And then once we're done, we now go load the data from the NMIS 8 var directory. So now we're talking to the device through the abstraction using our modeling. And again, all of that happens in a heartbeat. So the main structure for a model is that we start with the common section, which defines all of the common things that we want to load. And there's lots and lots of common things we're going to talk about in a second. The system section is then the next section, and that has a bunch of standard sort of sections that we use. And you can add sections to the system section that they're not there. These are some of the common ones. Node health is the most common. MIB2IP is reused a lot. And there's many other sections there, but we've got, we'll talk a little bit more about this as we go forward in how we do modeling, but they're the flat sections of the SNMP MIB. Interface section is really, really common. Almost all devices that talk SNMP collect data about interfaces. So we have the interface section, and then we do in-out octets, packets, packets HC, the standard ones there. We have a storage section, and then we still have this device section. It's used a little bit less often these days, generally speaking, and lots of things are now in the system health section. So the system health section is really where we do any new modeling for, sort of standard objects that are abstracted in SNMP. So when we're talking to things in SNMP, we'll usually be using the system health section. So here's some of the standard common models that ship with NMIS. There's actually a lot more than this now. That the list is so long, I didn't bother to put them all in. These are the most commonly used or reused ones, and some of these are sort of, as I've said there, the calls is much less used today. It was very common for monitoring modems back in the old days. But CBQoS in and out, which is for Cisco CBQoS, and then the database which is used by everything. The event model, common model, which is used for everything. Headings, stats, again used for everything. Heading is the names that we use in the graphs. Stats is a very powerful mechanism for doing maths and extracting data out of NMIS, along with any maths that you require done on that data is on the fly. So basically a pipeline system. Summary is then the how to generate the summary data that we might need, and then thresholds are all of the policies and related things for thresholding data out of NMIS. So that's the standard common models. We've now got heaps more. There's like the entity MIB's been modeled, so you can reuse that everywhere. We've got CDP, LLDP. The list is almost endless with the number of common models. Moved a lot of stuff in 8.6, we moved into common models just to reduce help the maintenance of the models and improve reusability. A lot more things are into models. So there's some Cisco common models, vendor-specific common models as well. So there's a bunch of Cisco-specific technologies. MPLS was a big thing that we've done with modeling, and they're all in the common model. So lots and lots and lots of things available there. So how do we model a device? The first thing we want to do is collect the information from a device, and we want to find out the supported MIBs. The best thing to do is to get an SNMP walk, and then we review the MIB data for elements to collect. So let's run through that process. And we'll start with decoding a MIB, because this is actually fundamental to how we do what we're doing when we're talking about things. So in the example that we're going to look at, we found this little device that was just didn't do too much. It just did some power monitoring. It was called an Emerson Network Power. That was the name. And we found these couple of voids here. So we did a little SNMP walk, and we think that those last three elements are quite interesting. So how does that work? So the first part there, SMI Enterprises 6302, is what we call the enterprises part of the MIB. That always translates to 136141. This is part of the SNMP tree, which we'll see a little diagram in a second of how that looks. And we're interested in those three MIBs. So we want to go find out information about them. So we Google those three MIBs. So we started sort of with nothing. We're just talking to this device. We don't know what it is. We've done an SNMP walk. We've got this information. We're now sort of doing some detective work. So now we Google. We just now Google the enterprise side. We find that that's the Emerson Energy Systems. a little bit more detective work, we find the EES Power MIB. And I think when I did this originally, it took me maybe 5 minutes. And then we find the vendor, and we found that we could download the MIB from the software support page. So now we've got the MIB. Now we can decode the data. So let's have a look at that MIB. I've just sort of, the tree is a really simple way to see this. So we've branched into the tree. We started with the ISO, so we've come down this tree, ISO, org, Department of Defense, Internet, Private. You've got to remember all of the stuff started from DARPA, so we're still all mapped under the Department of Defense. IEEE has a separate branch at the top level, but all the main stuff is under Department of Defense. Then we go to the enterprises. We're in the private branch, we're in enterprises, and we're in the EES MIB. At this point, the vendor publishes the MIB. We've left the standard MIBs, and we're now in the public MIBs, in the vendor MIBs, the proprietary MIBs. Their MIB structure now, they have a section called Global, which is identified by 2. Then they have the Power MIB, which is identified by 1, and the System, which is 2. So that's the branch we're following: Enterprise, EES, Global, Power MIB, System. And we discovered that their system voltage, system current, and system used capacity. They're the 3 things that we wanted to talk about and look at in this thing. So how do we actually get that data? We get that data, and what does it look like? So this is the actual MIB, the first section of the MIB that's relevant. We downloaded the MIB. We have a look through. SNMP MIBs are written in ASN1. ASN1 is abstract syntax notation. It's a formal language for describing data. It's very, very powerful and is used in many things, but it's most famously used in SNMP MIBs. So that's the structure of the MIB. So EES is an object identifier, which is under the branch of enterprises. Global is under the branch of EES. Power MIB is now the main section. It's under global and system. And then now we look at the next section, which then tells us it's the actual names of those objects. So now we're looking under the Power MIB, systems under the Power MIB, and then we're looking at system voltage, and it tells us that this is system voltage stored as millivolts, I assume, and included positive or negative, and the integer, which is basically 31 bits, 2.1 billion, represents an invalid value. So that when it's -1, basically, it's an invalid number, an invalid object. So that's how we sort of look at a MIB. MIBs are quite interesting things. I've been working with them for a really long time, and they're very, very powerful. I've also published a set of MIBs up on my GitHub that are quite useful. I've been collecting these for a long time, and I try and do my best to keep them all compiling and working. So I've had to edit some to make them compile, because some vendors out there don't sort of maintain their MIBs. But they're all basically up on my GitHub page, Casey Sinclair, up on GitHub, and they're all. It's all the Cisco ones. I try and do my best to keep it up to date. But MIBs are a whole big topic. We'll go back to modeling now, but this is the data that we're dealing with. The most important thing about MIBs is that there's the MIB file, and reading the MIB file and understanding the MIB file is very important. Loading those MIB files and getting SNMP walks with the MIBs intact really help you to understand the data. So let's talk now about adding a new device model. So we've got some new device called FUBAR that we want to add, and the vendor ID is 424242. And we've seen that the sys description is device FUBAR and a software version. So now I've looked up the enterprise number. We found a matching vendor name, and we're going to add an entry to the NMIS, enterprises.nmis, add an entry to the model file. We're going to decide on a new name for the model. We're going to copy an existing model, and then we're going to edit and update the model. So the first step is we open up the NMIS enterprises file, and we add in a new section, and we can put that at the bottom. It's no problem. It doesn't have to be in order. We just put that in the bottom of the file, making sure the commas stay intact, and we add 424242 with an OID 424242 and the enterprise name, vendor name, which might be in our case FUBAR vendor. Now the next name, vendor name, we've gone into the model.nmis, and we've added a new section called vendor name, and we've put an order, and we've put and we're doing these in order because these are rules. As soon as we hit one of these matches, we're going to stop processing. So what we're doing is we're adding one called device FUBAR when we're comparing that, we're going to match that text with a regular expression, and then we're going to use that model name. So we match that text and use this model name. Then we come down to the last section. We copy a file. We copy an existing model. You can copy almost any model you like, but the default V2 is a good one to start with. A default V2 is a good one to start with. So the node type is, in this case, I've just said it's a switch. That can be any number of different names. The vendor name is node vendor, and the model name is model name, and that needs to match. So if we've called this model name, the file needs to be model-modelname.nmis, and the node model needs to be node model name. So that's it. We've now created a new model for us to use. So let's look at a real example, Sun Microsystems. So we've gone and found out that Sun Microsystems is, enterprise ID 42. So we've gone and added that in. It's actually already there, of course. And Sun Microsystems, we usually see the words Sol or Sun SNMP or Sunos. And we're going to use the model called Sun Solaris if we see those. And then down in the actual Sun Solaris MIB, we're going to see node vendor is a server, node type is a server, node vendor is Sun Microsystems, and the node model is Sun Solaris. So there's a made up example and a real example of how that works. And now we've got a new model file that we can do things to talk to this new product that we've just obtained from somewhere or other. So the best thing to do is to use an existing model for a device. In the case that we've done a match, we've discovered that this Solaris device actually looks pretty like a NetSNMP device. So we just need to tell the system how to use that. And this is really common, this NetSNMP model. So for just a quick bit of history about NetSNMP, the NetSNMP project started as CMU SNMP, then it became UCD SNMP, so that's Carnegie Mellon University, then it became UC Davis, University of California, Davis, and then it just became unattached to the universities, probably still maintained by the same guys, but it's now called NetSNMP, and it really is the gold standard for SNMP. They have an excellent SNMP agent they provide for free. It's the standard SNMP agent on all Linux servers, and is also available, for example, if you want SNMP on Mac OS and just dozens of other operating systems that run Unix, you're looking at NetSNMP. And then many security companies now, because they're based on Linux, will start their SNMP modeling with an NetSNMP model, which is great. NetSNMP supports the host resource MIB. Windows supports the host resource MIB. NetSNMP includes a whole bunch of other really cool things in addition to the host resource MIB. So it's a very, very good model to start with, and lots of devices that we find are based on the NetSNMP MIB. So when you're using a server, you could just go ahead and reuse the NetSNMP one and basically tell the system to just go ahead and use that model. So what you would do is just actually go into the, you find out the vendor, which is NetSNMP, so we know that. We go to the enterprise, that's already been done. Now we go into the NetSNMP section of the model.nmis file, and this is for the auto discovery, and we add in SunOS. So we add a new section in there, and you can see there that Linux, SunOS, and Darwin. Darwin is for Mac OS, and then that just tells NMIS that it can go ahead and use a NetSNMP model when it's talking to Sunos devices, and that works really, really well. So that's how we can. So for nothing, literally for a few minutes work, we've now added support to a device that exists and can use an existing model. So now we want to add a new metric. Someone's come along, or we've figured out that there's a nice new metric that we want to get some data for. So, and we want to just add it to an existing node health section. So the example here I'm using, there's a really nice MIB that we've actually already modeled in NMIS, and it's included, but it's called, it's the number of routes that a device sees. So looking at MIB dumps, and again, something that I do because I'm an SNMP nerd, I've collected MIB dumps from devices just to keep them for reference to see how well MIBs are supported across many different vendors. And I've got directories full of them, megabytes of them. And so when we look up this MIB, there's two MIBs, and they both supported, and they're just slightly different numbers. But one was the IP CIDR route number, and one's called the INET CIDR route number. And different vendors support different ones of these. I think the preferred one is actually the second one is the preferred one. And the OIDs for those are very similar. So there's the OIDs, and we're now going to add this in. I'm going to show you how we add this into an existing model to be collected. So what we do is we did a little bit of detective work. We figure out which one of those is better supported. Basically, you can see here that it appears fairly obviously that the IP CIDR route number is the one that's better supported across all these different products, all these different vendors. So what we'll do is we'll add it to Cisco routers first. We have some implementation decisions to make. We need to make a decision what we're going to call the new metric. So we're going to call it, I like to base variable names on the MIB names. Route number looks good. The MIB name is called IP CIDR route number. The OID is 24.3, and we're going to call the graph name route number. So that's the key decisions. That this one was pretty straightforward. Sometimes it's a little bit harder to make those decisions because the variables are not quite as often. I might have multiple graphs, but we want to use meaningful names that help people to understand, because when you're dealing with this modeling, there's a little bit of user interface. So some of the names you're using, people are going to be interacting with in the GUI. So you just need to keep that little bit of usability in the back of your head. So we're going to need to make the following changes. We're going to add it to the model Cisco router to tell it to start collecting. Then we're going to update a common heading. Then we're going to add an entry to the NMIS OIDs so that we have a MIB file, and that file name is actually wrong. Sorry, that's actually nmisoids.mib, and then we create a graph to view that graph. So we're going to go step through how we do all of this now. So the first thing we do, we open up the model Cisco router, and we're going to add this little section here, and this is all we have to add to the system. We have a variable called route number, and the OID is IP CIDR route number. That's it. That's all we've added, and we've decided to add that to the node health section. That's an existing thing that we do for different devices, and we're going to store this as part of the node health data. So we're not creating a new RRD file, we're just adding it to an existing one. NMIS will automatically see that and automatically update the RRD file with the new variable, automatically. No need for us to worry about that. So we're just going to go in, we're going to add this new thing called route number, and now we need to tell the system what the graph heading is. So we've just got to go in into the common heading, and we tell it that there's going to be a graph, and the graph name is actually going to be called route number with lowercase, and so that needs to match. So we have a graph type, and it's going to be number of routes, and again that's going to be shown in the GUI as the headings where we've displayed this graph. And one thing I forgot to mention there, sorry, is graph type. We want this graph type to display we're telling NMIS that there's a new graph that we're creating that we want it to make available in different paths. So that's that we add route number to the graph type. Very important step. And then we go and open up the NMIS OIDs file, which is a user local NMIS 8 MIBs, and it's actually nmis_oids.mib. I'm going to fix up that name, and we'll get these slides out to everyone. But we just add an entry and just saying IP CIDR route number is this OID. It's just so we don't have to load and compile MIBs all the time. We just ship pre-compiled MIBs as OIDs. You don't actually need to use, and we're going to do this later in the modeling example, you don't need to actually use the name. You can actually just put the OID in there if you want to as well. Just sometimes that's faster for people. And often when I'm doing modeling now, I just put the OID into the model, and I just put the name there as another field called MIB name. So the next section that we have to do is we've I don't know, just like I've done here in the example, sorry. So if we wanted to, we could have just said IP CIDR route number, and just put the OID directly in. Now there's a funny thing going on here. We automatically append zeros and manage these things. So depending what you're doing when you're typing SNMP, sometimes you have to append a zero on the end, so .0, and sometimes when we're talking to certain MIBs, we don't need to, and NMIS actually helps you with that. So look at the examples exist, but there's an example where you can, as I was just describing, where you can just use the OID directly. So the next thing we have to do is just create a graph. Now this is a very simple graph to create for this particular one. let's not get too caught up on these things. Reverse Polish notation is actually fun, whether you believe it or not. So what we're doing here, because we use RRD, think of this is basically, we're writing a query, if you like. We're writing a query, but we're sending the query is to RRD. So we're sending all of this data in the option section. This is a standard graph and a small graph. We're going to send this data to RRD, and RRD is going to run these commands and give us back the graph. So it's really simple, and it's very, very powerful, and it's ridiculously fast. One of the reasons we use RRD is that I don't think there's anything faster for handling time series data and for generating graphs and doing the kind of maths that we want to do. It's just very, very powerful and very straightforward to use. I wouldn't say that it's simple, but it's very, very, once you understand it, it's very, very powerful. So fortunately for you guys, we've already understood it. We've abstracted a lot of this, and you don't have to deal with this stuff very often. So first thing we want to do is a definition. We're going to define an object called routes, and it comes from the variable called route number. And then we're going to define a line called routes, and it's the number of routes, and it's going to be colored blue. And then that's 000FF. Then we're going to print out routes, average number of routes, and we're going to format that as a two decimal places. And we're going to have the max number of routes. I'm going to print out the max number. That's really how simple, and that's how you interpret these things. There's lots and lots of examples of graphs. I never ever start a graph from scratch. I always look at something else and use something. And this is a very simple graph. We're not doing any maths. There's no maths we need to do. This is a gauge. We're just getting the data out and putting it onto a graph. And this is very straightforward. Most of the time, this is all your graphs have to be. If you're doing some maths, then you have to do what's called reverse Polish notation, which is the way that scientific calculators used to work. You would put numbers in, then to have an operation. So you punch a number in, enter, punch a number in, enter, punch a number in, enter, and then you do plus, and that would add all of those numbers together. So you push numbers on the stack, and then you push an operation onto the stack, and then that stack is executed. And the reason we do this, and the reason that Tobias chose RPN, is it's ridiculously fast, and it's really hard to describe how fast RRD is. It does literally tens of thousands of operations in a few seconds. It's just, and we see that all the time in NMIS, because NMIS is using it to grab data and crunch data. So when you display things in the GUI and you're doing lots of things, we're hitting RRD data to get the data out and display it to you, and it's just ridiculously fast. So that's why we're doing RPN. You know, if you're wondering, why do I have to deal with this obtuse reverse Polish notation? That's why. It's about speed and performance. So if you want more information about RRD tool, it's very, very powerful. The documentation is excellent. The two main pages that I find myself reading when I have to, and there's the defs and the CDEFs. There's a tutorial page there, and then the RPN pages. They're the two probably main pages. The RRD documentation is excellent. RRD is incredibly widely used. It's an excellent open source project, and it's been going for a really long time, and was right there. And the reason I was able to write NMIS at the end of the day was because I didn't have to solve the problems that Tobias had solved with RRD tool. I could focus my efforts on an application and use RRD as the performance database, and that's why we're here. Okay, so we've added something simple. So now we're going to go ahead and add something to the system section. So we want to collect something. We've been looking at a new thing. It's a relatively, and this is actually already in NMIS already now, but we decided that we'd look at TCP. So now system is what we use for doing flat things, and system health is what we do for using table constructs. A little bit more detail. We'll answer any questions you've got about that at the end, I think. But when I look at MIBs, and we'll show an example here in just a second, you'll see that that's why we would use the system section. So TCP is actually already included in the ModelNet SNMP, so you can go and look up how all of this works. It's really broadly selected. It's a standard MIB across many different devices. It's part of the standard RFC MIBs for all devices that are talking TCP. And the steps that we add a TCP section to the system section, we add any required MIBs to the NMIS OIDs. which is optional, but we can add them in. We add update common heading and common database, and then we create a graph to view the two things that we want to do, connections and segments. So if we do an SNMP walk, this is what the MIB looks like. Now, when I see objects like this in a MIB that end in 0, that means that they're a flat section. There's no children, there's no construct. This is just name value pairs essentially. So this is just, this device has one set of name value pairs. There's no repetitions. Interfaces would be tables. So if I have a number of interfaces in a device, I would have a table of interfaces. I only have one set of TCP counters. So this is what we call a flat section of SNMP MIB. And you can see here we've got, for example, and these are combinations of counters and gauges. We'll talk about that in a second. But there's current established is a really great one for SNMP. That's how many current TCP sessions this thing has established. A very, very good metric for many, many reasons. Great one for security, for example. So we'll just we're now going to go into and add a new section. So we've gone into the system part of the MIB, and we don't need to. We just go and add a new RRD section. This is really straightforward. We're just going to be collecting a new set of RRD data called TCP, and we're going to have a graph type called two graphs called TCP con and TCP segs, which is connections and segments. And then we're going to add in the SNMP that we need to do. All of these MIBs were actually already in the SNMP, the default NMIS MIBs anyway. But I've got TCP active opens, TCP passive opens. Now what's important is that some of these are counters and some of these are gauges. I won't go into the details of that right now, but you need to identify if something's a counter, the SNMP MIB will tell you it's a counter, and you set the option of counter. And you can have upper and lower limits, and these are some more advanced features, but typically you would just go and put counter and you put 0U, so the minimum value you accept is 0, and the maximum is unbounded. And for a gauge, in this case, could be any large number, so we just go, minimum value we accept is U, and the upper is unbounded. So, but a gauge is face value. So if I'm sitting in the dashboard of my car, so I'm sitting in my car looking at my dashboard, my speedometer is a gauge. So it's telling me right now, when I look at that, I'm seeing that I'm doing 60 miles an hour, 40 miles an hour, 100 kilometers an hour, or 40 kilometers an hour. That's a gauge. It's the speed, it's the measure right now. The counter is the odometer. As I'm driving and I'm clocking over those kilometers at 40 kilometers an hour, quite slowly, that odometer is the number of kilometers I've traveled. So when I look at it, I look down, I see a counter, and I've done 1,300 kilometers. I look away, 5 minutes later, I look down, I've done 1,300 and whatever, 302 kilometers, whatever the meters per second calculates out to be. So the point is, every time I look at that odometer, it's counting up. So to see how fast I'm going, I could actually look at the odometer now, look at the odometer in 5 minutes, the number of kilometers, do the math, and know how fast I was going, my average speed. And that's how all of this stuff works. That's time series data. So we have those two things. We have odometers, we have counters and gauges, and that's how we look at the different types of data. All right, so we have an odometer, a counter, we have a speedometer, a gauge, and that's the fundamental maths that are going on all the time inside NMIS and inside RRD. So now I'm looking at the other parts of the MIBs. We've added this already. This was already added into the MIBs for you, but there's just all of the interesting MIBs. So we've added those OIDs into the NMIS OIDs file. And now the last thing to do is to go in, or one of the things to do is to go and add the common headings. So now I've just gone in and I've got those two graphs. So I've just got TCP connections, TCP segments, again, part of the user interface for usability. I've gone into the common database. I've added a new database type. So these are that's the old paths, but you'll see in the new paths that's under the node. It'll be a slightly different structure these days, but I'll have a thing called TCP, and I'll have a way to tell it where to put the data. And we evaluate these dollar variables and fill those in an NMIS for you and name those appropriately. But basically that's going to drop that and create an RRD file for us. Now I go into the actual modeling for a graph, and I go and create in some definitions. And you can see here I'm doing a little bit of maths. I'm doing some in and output segments, and I'm doing them above and below the line. And I'm doing some, not really doing any much else maths than that. So here's a CDEF. CDEFs, I'm getting this value called TCP split, and then I'm putting TCP in segments, which was a definition here, and I'm pushing that on the stack, then I push -1 on the stack, then I push an operation, which is multiply those together. In this case, I decided to do an area and then a stack, so that looks like a nice graph, and it's very, very powerful. So that's a simple graph that we've done for getting TCP going, and the result is going back to those are these two graphs here, and these have been really, really handy for lots of things that we do when we're looking at server monitoring. That the TCP retransmitted is a great one. You should never have many retransmitted TCP segments and attempt files. Anyway, really fantastic data for troubleshooting network-related problems on servers. We'll just move on to the next section. I just need to pause, mute for 1 second. Okay, sorry, back on there. So system health section. We would use the system health section if we were doing some table construct. So in this case, the example we're going to do is a disk IO table. So this is something, again, we added to MS a while ago. So I have many disks inside a server. This was part of the UCD MIB, the very, very powerful MIB that tells us the disk activity on a server. So number of bytes read and written, and the number of blocks that we've read and written to a disk. So very, very powerful information. So they're the steps that we're going to go through. What does the data look like? So for each disk, we have, for every single disk, you can see the index here is .26. So I've got an index. This is a really standard MIB. This is a really nicely structured MIB. This is the way all MIBs should be structured and written. Unfortunately, not all like this, but most of them are. There's a few exceptions. So we have device name, we have a counter for the number of things read and written, and the number of writes, and we can see here there's no gauges at all. And we actually really want to be using this these last two here, these 64-bit counters at the end. So how do we now use this? So we go in, we add a new system health section. There's two parts of the system health section. There's a sys part and the RRD part. The sys part is written when we do an update. An update, when we run an NMIS update, that's a discovery. So we run the, it's going to do many things that we want it to do, but it's really about discovering what's there, and it's going to be some data that we use in the GUI as well. Then the RRD section is the data that we run every poll cycle. That's what we're going to actually poll every single, well, whatever it is, 1 minute, 5 minutes, etc. We're going to go and collect that RRD data and shove it into the RRD. So basically, we've gone through the other things that we need to do, but these are the top level constructs. We're going to drill into a little bit more detail in a second, but these are the top level constructs that we need. We need to have the disk IO table, the disk IO index, and so forth. They're really critical names. So the indexed is the variable that we're going to use to index the data, and the headers are the things that we're going to display in the GUI. The disk IO table, we're going to have a control, so we're only interested in things that are the word SDA, SR, or disk, and this is an index thing, and we're going to create two graph types, disk IO read write and disk IO read write bytes. So now we sort of go into a little bit more detail about how some of those things look. So the sys section, we want to get the index and the device, and we're going to go and collect those bits of information, but we're only going to display in the GUI the headers field, which is disk IO device. And then the title is what we call that field if we want to display it in the GUI. So in the RRD section, we're looking at, again, just like the other things that we've already been modeling, we want to go and collect disk IO read X and disk IO written X, and these are counters, they're unbounded, and you don't actually need a title here, but it's nice to sometimes write notes to yourself, messages, but then that title in the RRD section is never going to be displayed. So this is the actual SNMP gets that we're going to do on the poll cycle. That's an important thing. And then if we don't already have them, we've got to go and update the NMIS OIDS file with the relevant MIBs that we have to collect. And we update the common headings with the heading names for the graphs so that we display them nicely. If you don't do this, you'll just see heading not defined in model. You can just go ahead and do the headings. So now we've just got to add one more thing into the common database, and that gives us the disk IO table must match the common section. So we go in and we add a section called disk IO table, and then we go and define the path where we want to store that file. And that will now grab that file and store it. And we can use variables, and the indexes, these are all standard variables, and we'll talk about those in a second. Then we go in and create a graph. Again, this is a very straightforward graph. No maths to be done on this one. So we just grab the values out and we just draw them. We just gprint them. And we add a new section. So the other thing that we did is in the system health section, we just told the system health for this device to go and do this disk IO table. And we do that just to give a little bit more granular control over system health. And it tells NMIS that there are system health sections to look for and then to go and get that data. It's just a little, it's an optimization that's quite important that we include in there. So the result of that is that now, when we've done all that correctly, we end up with an automatic menu item created in the GUI for us called disk IO table, and we end up with some nice graphs there, and you can see that these always been running for more than 2 days. But we've got the primary disk in Linux would be SDA and SDA at SDB. So we've got SDA there, which would be the root volume. But this is the device names. These are mapping the devices, not the file systems. These are about the device block level and bytes read and written to the disk. Okay. I'm just moving through this probably fairly fast at the moment. Normally we would go through this a bit slower, but we wanted to make sure we could fit it into the webinar. So I'll stop for questions at the end. But we'll talk a little bit about device model plugins. Plugins got added into NMIS fairly recently in the last couple of years, and these have been incredibly powerful. There's 4 types of plugins. You have an update plugin or a collect plugin. They'll run after on a node. So when I'm dealing with a node, I'll run an update plugin after an update. I run a collect plugin after a collect. It's really important to note that while the node is in memory in NMIS, I've polled the node, I've done all the other things with SNMP and WMI, I've still got everything loaded in memory. I now go and run the collect plugin, for example. I now can go and do anything I need to do, manipulate the data that's already in memory, and then I can save that data. I can do all of that in the plugin. The plugins are incredibly powerful. We had a bunch of, and the reason we did this was that we had a bunch of these crazy things that we needed to do in SNMP that just were non-standard. So people interpreting the standards unusually and doing unusual things with SNMP and other things that we wanted to talk to. So we just needed something that covered 100% of cases. So we went with a plugin. Plugins are written in Perl, and they're essentially anything written in Perl and available to you, and you've got the NMIS API available to you inside that plugin. You can do just about anything. So if you need to manipulate data, collect more data, we had some crazy ones where the SNMP indexes were back to front. So the net result is that you can see examples of all this in the source code, or they're all shipped these examples. But basically we had to build this index on the fly. It wasn't something that SNMP actually told us directly. It was very unusual. So we had to go and use a plugin to go and collect that data and store it. That was for the some Ericsson gear that we were talking to. And then other examples have been where we've had just all sorts of crazy devices that we've had to talk to. But we can also go and collect other devices. So recently a customer just did some stuff with netconf. So they did some basic modeling to get the structure, the scaffolding inside NMIS. Then they use a plugin to go and use netconf to pull the XML data, parse the XML data, and store it in an RRD file every 5 minutes. And that's because that particular vendor had some SNMP support, but they decided to put their performance data in available through netconf. Just want to point out at this point, one of the reasons that SNMP is so good is it's super, super blindingly fast. Thousands of polls per second that you can do with SNMP and collect lots and lots of data really, really fast. Protocols like netconf are not fast. They're not intended for polling every 5 minutes, right? So these are not great ideas that vendors make for storing data in using protocols like netconf because of all the overhead involved in those protocols. Very powerful protocols, very good protocols, not intended for running every 5 minutes. You can, and it works. It's very difficult to scale. So you can basically get access to just about anything you want to do, and then you can save performance data, inventory data, whatever you want to do, and it really comes up with handling everything else. We're not going to go into details around plugins today. It's what I'd call an advanced feature. If you've not done Perl coding, you go and look at existing plugins and modify them, no problem. And we use them to embellish data. We use them to just tweak things and make cross references between objects and do some interesting things. And there's lots of examples of plugins, and that's the best thing to do is start by looking at the plugins directory. Let's talk about thresholding. So we'll just add a new, we've collected some variables, now we want to do some thresholding. So what are the steps that we have to do? So what do we want to threshold? Does it make sense? We're going to have to put the event name is going to include a proactive at the beginning, so NMIS knows how to handle it. So that's a sort of an unwritten rule, but if you're going to do a threshold and you don't put the word proactive in front of it, you know, we'll do some default things with threshold events if you use the word proactive and take care of things for you. So in this case, we're just going to do some environmental temperature things. There's an RRD that's already been collected. It's called system health. And we're going to have a new threshold. So we go into env temp. It's under system health, and we've got a thing called env temp. Then we add in the common thresholds. We go and add a section called env temp, and then the event is called proactive temp, and the item is called current temp. Then we add the statistics section, which is down the bottom. We go into common stats. We add in env temp, and then that we have a variable there called current temp. That variable current temp matches the item name current temp. So the thresholding system is going to execute the stats, get that data out, compare it to the thresholds, and generate the event if it crosses the threshold. It's a lot going on there, and a lot of stuff's done for you. But that's the three constructs that you need. You name a threshold, then the env temp is then that name of the threshold is then used. In this case, it's the same as the actual section name, but we're using that env temp name. We've taken env temp. We've got an event name proactive. We've got this item name current temp, and then we're matching that data together, and that's how we use the data. So to run thresholds, we can then test the thresholds. What I do is I just go and set them to be very, very low, like even 1 or something, and I just verify that the threshold's firing. So I just do, and I can do nmis.pl type thresholds, debug true, node equals router 1, and then run a specific threshold on a specific device and just test my thresholds. I change warning to 5, and then I change it back up to 50 and just see that the threshold opens and closes and the event opens and closes. And I can do, controls are all through NMIS, and they're very, very powerful, and we have access to these variables. There's many more now that are available, and there's documentation on this on the wiki page. But basically, what we want to be able to do with thresholds is be very specific. So I might want to have very coarse or very less strict CPU thresholds for core devices, but higher values for maybe access and default access and devices. So I'm more concerned about CPU load on my core devices than I am on the rest of my devices. So that might be a way I can do it using a control. We've got heaps and heaps of sample controls in there. There's interface speed specific ones for interface utilization, for example. There's lots of different node type specific ones. So you can look in the thresholds NMIS and you'll see examples of those. Custom alerting was added into NMIS reasonably, well, I guess it was 3 or 4 years ago now, but seems like it was pretty recent. And there's a whole document there on how to do custom alerts. And these custom alerts are there as just another way to do very simple things in modeling without having to do maybe a full threshold. You just actually want to get an alert when a fan fails. So that would be raising an event, or what we call an alert. And that's very, very powerful, all documented there in custom alerting. So running and troubleshooting, the most important 2 commands are update and then model true and node, and you can also use debug equals true as well. And then you'll get some really good output like the example here. It just helps you to see what's going on. When you're doing this sort of stuff, you need to set a little bit of time aside. And then what's important now is we also do what thing called model caching. So you need to, when you run an update, the models are recreated. So if you've been editing the model, you need to then just run an update to sort of force a recompile, or you delete the cached model. And I've just put in here about the debugging device modeling, which we just talked about, and you'll look for RRD updates, and you'll see those there. And they'll help you understand what data you collected, what you're writing. So very useful. And then you can always look in the node file to see what's been collected. So now we're going to open up for any questions. Sorry that it is a big topic. We've gone right on 55 minutes. So it is a huge topic. We felt it was an important one to cover and to just show that it's possible. And I think there's a saying in Perl that Perl makes the simple things possible, and the simple things easy, and the difficult things are possible. And that's a little bit what modeling's like. To do simple things in modelling is quite easy and straightforward, but it actually makes bigger, more complex things that you might want to do, tackling collecting device data. It is possible, and it can be done. And we've got all the mechanisms there to support it. And if it's standard sort of SNMP modeling, it's very straightforward to do in the models, and you don't have to do any of the plugins or anything fancy. We've had a lot of customers write their own models and contribute them back to the community as well. So it's something that we're very, very happy with, that we've got such great device support through the modeling system. So is there any questions at all? I'm not really great with the GoToWebinar, so I'll just figure out how to answer questions. Mark, if you could give me a hand answering questions, or how do I ask for questions?
Sure thing, Keith.
I'm not seeing
anyone who wants to ask questions, we can take them off mute. Usually at this point, Keith, I stop the recording. That way, if anybody wants to ask a question using their microphone, they're not recorded.
Okay, I'm going to stop the recording.